Hi everyone, welcome to the 10th lecture of Spatial Statistics and Spatial Econometrics. In today's lecture, we are going to sort of shift gears to working with data. And any time that you work with data, the first step is exploratory analysis. So what you really ought to do is to be able to summarize these data or explore, conduct an exploratory analysis intelligently, so that you can start to discover patterns that that are in these data, right? In the data that you're working with. What do we typically do when we sort of do exploratory data analysis? We begin by plotting histograms. We try and look at the shape of the distribution. Are the data symmetric in their distribution? Are they skewed towards the right or skewed towards the left? That is to say, are there more extreme outlier values on the right hand side of the distribution or the left hand side of the distribution, right? We also summarize by documenting the mean, the sample mean, the sample variance, the minima, the maxima, the 5th percentile, the 95th percentiles, things that you have heard of till now in this course, already. Okay, we want to now sort of understand when we get data that are georeferenced, that is to say that they have location coordinates. I mean, they could be lat long coordinates, they could be simply xy coordinates. You may not be working with data that are necessarily geotagged, but they have some tag of a location, right? Whenever you get data that are locationally or spatially delineated with whatever spatial system that is used to create these coordinates for these data in the dimension that you are working in, how do we go about conducting what is called as the exploratory spatial data analysis, right? How would it be different from a typical exploratory data analysis? Obviously, as a first step, location is going to become a marker to which you are going to summarize the data, right? So now your means and your variances are not just sample means, but they are sample means in the east-west direction versus the north-south direction, and so on and so forth, right? Because we are studying data analysis, we have to start with an example. So let's do that and go step by step, look at what do we look at when we try and sort of summarize spatial data in terms of exploration. So here I want to sort of first of all, these the example that the case that I'm going to use to introduce exploratory spatial data analysis is adapted from the book written by Noel A. Cressy, which is a 1993 publication. It is also a reference book for this course. So you can go back and you can read chapter 2 of this book. You must read the first and the second chapter at least of this book. It is a very well written book. However, it's a bit technical. So one of the jobs that I do through this course is to make this book a little bit more accessible to you as and when you start to read it, right? So let's look at the example that Cressy presents in order to explain to us what is exploratory data spatial data analysis and how to go about it. So Cressy takes his example of coal ash data. So what we are looking at is locations where we have samples of coal ash volume. So coal ash is the type of impurity in when one wants to mine coal from beneath the ground. You don't really know how much coal can be found just right beneath where I'm standing, and in this area, what is the quantity of coal, what is the quality of coal, and one has to be able to estimate this quantity and quality characteristics of coal beneath the ground before one invests in pulling the earth out and engaging in mining. Remember, coal mining projects are, often multi-decade projects, right? So when you go in, you really are going to be spending a lot of capital in terms of, mining that coal. So what one does is that, one has to explore whether or not there is coal beneath any particular region that we can look at, and what is the quality of that coal, right? I mean, you may have a lot of coal, but if it is not so good quality, perhaps you want to sort of prioritize mining in a different area where you have very high quality coal, right? So here is an example of a region which has been sampled for coal, right? And these crosses that you see on your screen are locations where cores are dug into the ground, and earth is brought out so that you can get samples of coal that will provide you an idea of how much coal is available and of what quality, right? Now, the first thing that we notice here is that we cannot get sample of every location in space. That is to say that we cannot be digging holes at every location in space, right? We can only dig these holes at locations where we see these crosses, right? So we only know what's happening beneath the ground at locations where we see these crosses. Everywhere else we do not see these crosses, where we have not cored or we have not sampled, we are still blind to it, right? So although I might get a very good idea of what's happening at this cross which I have circled with a red circle, or some of these crosses, I will have no idea what's happening in the region around these red circled crosses. And this is one of the roles of spatial statistics. This is one of the places where spatial statistics came into being, is to be able to predict the quality and the quantity of coal beneath the ground where it has not been sampled, using information from where it has been sampled. That is the crosses by themselves. So the idea is that we cannot go out and actually sample every location in space. It is extremely costly, it's almost nonsensical. It's one of the reasons why when India does its decadal census, it can only sample certain percentage of population. It is not possible to go out and collect data, survey data from every individual in India or every household in India, right? It's extremely costly and it's going to take a lot of time. Probably you will never be able to finish such an exercise. So we try and get a sample of some people, and our sampling strategy is usually smart, intelligent, it's driven by science, and using that sample we try and make inferences about the population. Okay. Similarly in space, here in this example, you are sampling certain points on the ground and you are leaving others out, but when you sample these points on the ground, the idea is, the purpose is that I should be able to predict what's happening in the region, in the larger region, using these many samples, sample points on the ground, right? If nothing, I should at least be able to say what's happening in, spaces within a smaller domain where I was not able to sample, although I have a very good sample. I mean, I think these are 294 sample points if you read the book. So around 300 sample points. But that's not sufficient. I mean, if I were to sample every point, I mean, there will be very large value, very large value, right? You can dig here, you can dig here, you can dig here, you can keep digging, as much as you would like, right? So that's where spatial statistics comes in, and as a first step, we want to sort of look at the data, summarize the data with the final objective that we will be able to predict what's happening in the region beneath the surface, so that we can make these production decisions, whether to go in or maybe move to a next location. Okay, so coal mining industry, oil exploration industry, and such, is where most of the genesis of geostatistics really comes from. Okay, so here is another visualization of the data. This visualization is now happening in 3D. In 3D, now your west direction which we saw on the map is now, let's say it is the x-axis, and the north direction is, let's say, the y-axis, and the z-axis or the z-axis, which is the height, is giving me the content of coal ash that is found at the samples that was drawn at each location on the ground, right? So my west is my x-axis, north is my y-axis, and I'm looking at a height from ground to sort of identify the percentage coal ash. Of course, the larger the value of coal ash, higher the impurity, and perhaps the lesser desirable this coal mining project will become, right? So let's move forward in the quest to summarize these data. So in the next step, what is being done is that this orientation in which the data were originally procured, it is then sort of reoriented in our typical row versus column or XY direction that we are very used to, right? When we study the graphs, we are very used to the x-axis and the y-axis. So we sort of reorient the original data set to be represented with rows along the y-axis, so rows along the y-axis, and columns along the x-axis. Indeed, the data were sampled in rows and columns, right? They were just, in an orientation in space that we could simply sort of, change a little bit, and it gives us a very nice XY orientation to start working with. Another thing in this representation is that instead of simply putting a cross, what we are putting are the values which represent percentage coal ash at that location, right? So at column 14 and row 23, the coal that was dug out or that was sampled had 9.99% of coal ash, right? In column 1, row 14, you had slightly higher percentage of coal ash, which is 10.21%. There are some locations where the coal ash percentage is quite high. I mean, we can go back and check. I mean, we saw a very high number here, which was closer to 17.6. Of course, that is to be found in the data set as well. In column 5 and row 6, you have this value 17.61, which is a quite high level of percentage coal ash, especially if you look at the samples around this particular location, right? If you go one step north of this location, you have 10.96, east is 10.87, south is 10.8, and west is 10.82. So somehow 17.62 seems like an aberration, right? So straight away, there is this inquisitiveness that arises when we start to look at the data closely, right? And we would want to then discover patterns in these data that that provide us information about the coal that is available beneath the ground in the region of study, right? Another thing one can do is that one could have a sample mean. So if I were given a non-spatial data, I will simply take all these values, sum them up, and divide it by the total number of observations. I'll get a sample mean. Here you can get a mean which is row by row. You can get a mean for row 23, for row 21, for row 20, all the way till row 1. And you can get a separate mean for column 1, for column 2, for column 3, column 4, column 5, column 6, and so on and so forth. So now you are getting these mean values in east-west direction and north-south direction, which are different, right? So this right away introduces the spatiality of the data, which is the spatial dimension of the data, to summary statistics. Just like we are evaluating means for different rows and columns, we might as well evaluate the mode, the median, the variance, the min, the max, and the 95th and the 5th percentile or other percentiles of our interest, right? So interestingly, when we look at the data right away, we are able to sort of, see these dimensions play out. So as a next step, what we start with is what we call as detecting outliers. And I'm saying detecting outliers 1, that is to say that's the first step towards detecting outliers. What I have here is called as the stem and leaf plot, which perhaps was the traditional version of a histogram. So if you look at the stem and leaf plot, the way it sort of turns out is a skewed bell curve. Pardon me for my bad drawing. But if you were to sort of take this this vertical stem and leaf plot and just rotate it to a horizontal stem and leaf plot, it will start looking like a density function or even something like a histogram, correct? So the stem and leaf plot, first of all, is just like a histogram. The second thing is how is it actually constructed? So the stem and leaf plot is constructed by taking each value in my data, rounding it off to the first decimal order. So let's say I have 11.17, that will become 11.2. I have 9.92, which will just be 10, 10.21, which will be 10.2. I have 10.14, I'm going to call it 10.1. Then I have 10.82, which will be 10.8, 10.7, 9.9, 11.3, and so on and so forth. So we collect all these values and we go from the smallest value, say 6, okay, and we go and figure out, do I have 6 with decimal entities 6.1, 6.2, 6.3, 6.4, 6.5, and 6, so on and so forth. I have in this entire data set, you can search and you will find there are no values of percentage coal ash being as low as 6%, right? So minimum that we see is 7% in this data. So in front of 6, we have nothing, no entry. In front of 7, when we move on to 7, we see 7003. That means in my data set, I'm going to have an entry which is going to be 7.0, another entry with 7.0, and then another entry with 7.3. I will have entries, 3 entries of value 7.6, 1 entry of 7.7, and then 4 entries of or 5 entries of 7.8, and then 2 entries of 7.9, and you keep on going. When you collect or organize or summarize your data in this fashion, you have a stem which is all the values in front of the decimal point, and on the left hand side of this stem and leaf plot, which is called as the stem, and the values on the right hand side, which is a collection, which is the frequency count using the decimal values, the first order decimal value on the right hand side of the decimal point, is called as the leaf portion of this stem and leaf plot. Like I said, we can simply draw a histogram and we will get the exact same understanding of this entity. The histogram that we build should be sort of binned with bin sizes of 0.5. So I should have 6.0, 6.5, 7.0, 7.5, 8.0, 8.5, keep going all the way to 17.5 and 18, right? And now if you were to do a frequency count and draw a histogram of these data on this value, you will get an exact representation that the leaf and the stem and leaf plot is providing in the vertical orientation, right? So you can replicate this. It will also be helpful to understand what a stem and leaf plot is. So using the stem and leaf plot, what we are able to understand is that the density of these values, density of these data seems to be skewed towards the right. So you have a very high value of 17.6, then you have some values at 12 and 13, and then most of the values are really sort of starting to pick up on the left hand side at 11. You have a mean around 9 and 10, so you have a large sort of distribution mass around there, and then it starts to decline, and this sort of dies out to the right. Okay, I've not done a good job of plotting the histogram, but the density will be skewed to the right. I think I should redraw this. Sorry about that fumble. So the histogram, if I were to draw it, it'll look something like the following. Okay, so you'll have your 17.5 somewhere here, and you'll have your 6 here, your 7s here, and so on and so forth. Okay, so the mode and the median probably will be, this one of the centrality measures will be around 9 or 10, probably 9. I think that's where the height becomes the largest, right? 9 or 9.5 will probably where you will find the median of these data, So we know for a fact that the data are right skewed, they are asymmetric. Of course, they are right skewed, so they are asymmetric in nature. And it's likely that the mean of coal ash value will be greater than the median because it's right skewed. So your mean might sort of come out to be around, I don't know, 12 or 13. That's going to be the mean. The median is going to be shorter because it's right skewed, density function. So that's the first step. Now here, clearly the values were so high as 17.61, we located it, seems to be a problematic value. So I will mark it using the stem and leaf plot or a histogram. I can mark the first potential outlier in my data. Okay, so I've marked the first potential outlier in my data. What's the next step, right? So here I'm just showing you in green circles, you have all the values which I thought when I looked at this histogram or the stem and leaf plot for the first time, which were potential outliers, things that did not agree with the larger region, the areas that did not agree. Now these outliers can come up due to different reasons, right? I mean, they could be because of measurement errors, they could be indeed be outliers by themselves. But these are troublesome values that should raise a red flag when we calculate the mean value, right? So if we omit all these outliers and we calculate a mean, it might be much lower than if we were to include all of them because they are all skewed in the right hand side direction or the larger percentage coal ash direction. So what it really means is that if you calculate a sample mean and if you believe it blindly, you might underestimate coal quality found in that region because the percentage coal ash or impurity will turn out to be much higher than probably what it might seem if you were to remove these 5-6 outlier values, especially the large one which is 17.61. Okay, all right. So detecting outliers 2 is analyzing the difference between the mean and the median. Okay, so when we looked at the histogram, we just saw that if you have a skewed distribution, the skewness comes from some values which are sort of outside of the domain of the larger, large amount of data. Those are indeed our troublesome values or our outliers, right? And what is the signal of a skew in the distribution? It is the fact that the mean and median are no longer the same, right? So if you have a symmetric distribution, like a bell curve for a normal distribution, your mean and median are going to be exactly the same. For a symmetric distribution, mean is equal to the median, right? So that is the symmetric distribution. But in case you have a asymmetric distribution, you have something like, in red, or let's say you have something like in blue, then you're no longer going to have your mean and median values to be higher, right? For blue, you're going to have your median to be smaller than the mean, and for the red, you're going to have the mean to be smaller than the median. So by comparing means and medians can help us detect outliers. It will be a signal again that maybe there are some outliers in the data that we should start to worry about. Okay. So first of all, so how does it sort of help us move beyond the histogram? I mean, histogram could also tell me that there is a skew, right? But you know, moving to this second step serves a couple of purposes. The first is that median is a resistant statistic. So measuring trends in data using medians is robust to any atypical observations or outliers, right? So first of all, the second step tells me that maybe you should always, you know, summarize the median of a data set whenever you summarize the mean of it, because the mean might be misrepresenting or confounding due to some values which are very, very high, right? For example, you know, income levels in India. If you look at the mean income levels, that is the average GDP or GDP per capita, that is the mean GDP level, it might be much, much higher than the median GDP level, because you know there are some individuals which may have a lot more wealth than, you know, all the other people in the country, right? So sometimes you know, mean values can be misleading, right? They can mislead you about the status of a given statistic that you are that you are studying. So whenever we summarize the mean, we should, as best practice, you know, as data scientists, as statisticians, applied economists, social scientists, engineers, we should always also look at the median value, okay, to get a full picture. Second, the comparison between the median with the mean signals skewness, something that we have covered before, and hence presence of atypical observations in the data, something that we have spent the previous 5-10 minutes thinking about. Okay, what this really is helping me do is to build a statistic in order to infer whether or not there are, you know, atypical values in my data, right? So what we say is that if the absolute difference, that is mean minus median, the absolute value of mean minus median is large enough, then a given sequence of spatial data points must be scanned for outliers. Okay, so of course, you know, we know that mean is less than median or mean is greater than median. Both are sort of signals of trouble. But then what is it, how far should mean be from median that should signal real trouble, right? So we want to sort of concretize this idea before we are sort of, before we sort of start scanning for outliers or become worried about outliers in our data, right? Even slight asymmetry will cause difference between mean and median, but maybe that's not something to worry about so much. So when you have a very large outlier, you're going to have the mean, you know, pulled away from median more and more, and after a certain point, it will be a sure shot or statistically, you know, significant signal for scanning for outliers. So what we really want to do is we want to look at mean minus median and its absolute value. Why do we look at absolute value? Because, you know, this is exactly the same as median minus mean, so it won't matter which way, is it a left skewed or right skewed distribution, it won't matter anymore. We just want to look at the distance between the two and figure out what this value should be that should signal trouble. I mean, trouble in the sense of outlier values. Okay, so let's move forward and take a look at it. All right, so what you see on this on your screen now is a separation of row summaries from column summaries, right? So when we looked at this data, when I presented this data to you originally, I had said that, you know, we can figure out means and medians in the east-west direction or in the north-south direction, right? So now the rows are indeed the east-west directional summaries and the columns are, the north-south directional summaries. So we look at the data. The way it's summarized is that, I have my data and it's in its shape exactly laid out here. So it's the same exact layout. What that really means is that the top row, which has 5 crosses, which has cross in the row, are basically representing 8.59, 9.00, 11.86, 8.91 and 9.99, right? The second row has 7 crosses, are basically nothing but representing values, 7 coal ash percent values in the second row of the data set layout, which is 11.62, 10.91, 8.76, 8.89, 9.10, 7.62 and 9.65, right? And for each row, when we say row summaries, what we are doing is for each row, we are documenting a median value, which is represented by the circle, right, and a mean value, which is documented by an asterisk, right? So wherever I see the mean is greater than the median, that should signal right skew. That is, there is some value which is quite high on the right hand side of the distribution. So let me look at the first row. I have 8.59, 9.00, 11.86, 8.91 and 9.99. Quite clearly, this value, which is closer to 12, is 3 points higher than most of the values, are 2 points higher than 9.99, which is quite a bit if you think about it, right? So 3 points higher than 9.99 is 33% higher, right? 2 points higher than 10 is 20% higher. So 11.86 indeed is a value which is quite peculiar or different and quite large, given that it's right besides these values on the same row where we are sampling coal. Keep in mind, we are sampling coal, so it's earth. How different will it be if you're walking on this row number 23, and you walk on the first 2 values, they come out to be 12 or to be 9, closer to 9, and the third value that you walk onto is 12. Then the fourth value that you walk onto is again lower than below 9. So this sort of signals that there is some peculiarity, seemingly some peculiarity about 11.86. Similarly, we will go from row to row to row to row, and for each row we are going to document the mean and the median. Wherever I see mean and median to be very, very close, those represent symmetric distribution. Places where I probably shouldn't worry too much, it probably seems like there is no trouble, right? There is no worry, right? Places where we have very large differences are places that we should start to worry about, right? We will do the same thing in the north-south direction. Again, if I come back and look at, I'm going to start with this particular column. It only has one value, so no surprises. Mean is exactly equal to mean. Mean is exactly equal to median, right? So perfect. Okay, let's go back to the problematic value where I had 11.86, which is column number 3 from right. Okay, let's look at column number 3 from right. So I'm looking at, I am looking at a large difference between mean and the median. And if I look at this column as well, I have 11.86, that's my first step in the south direction starting from north. And as I take my second step, I go down to 7.62, which is quite a fall if you think about it, right? It's almost a 40% fall. Then I go to the next step, I'm at the same level, similar level, 7.61, same level, slightly higher, quite high, 9.58, come back to the same level, 8.64, and then 7.83, right? So this column seems peculiar and seemingly problematic. So we should now we are now starting to sense some outlier behavior by 11.87, right? So we are going to do this for each of the row, right? Now we can't be looking at each median and mean and each row and each column one by one, and it's very time consuming. Secondly, whether or not the difference between mean and median is large enough to signal trouble, well, it's highly subjective on the analyst. If I am analyzing these data and I feel that the distance this big is large enough, then it's highly subjective. Now, when we do science, we can't rely on subjectivity of the analyst, right? We have to come up with an objective measure which can, provide us a somewhat definitive understanding of whether or not, this much distance to say signals trouble. Okay, so that's that's our basic quest going forward. So when we do that, we are going to develop a theory to be able to figure out how much difference between mean and median is a large enough difference to signal outlier values. So let's say we have a sequence of data y1, y2 all the way through yn, which is independently and identically distributed with PDF f of y with parameters mu and sigma squared. Quite likely a normal distribution, right? I mean, it's a Gaussian. That's why we have a mean mu and a variance sigma squared. The sample mean is denoted as y bar and sample median is denoted as y tilde. We can write an approximate relationship between mean and median, right? So Cressy sort of provides, as I said, this is all adapted from a chapter 2 of Cressy's book. So you can go back and look at this relationship, but this relationship really provides an analytical link between the median value y tilde and the mean value y bar, which we'll see in a minute, but it says y tilde equals population mean mu plus 1 over n summation I equals 1 to n sine SGN means sine of yi minus mu. So I'm not really documenting yi minus mu, but just the sign of it, right? So if yi is greater than mu, I just have a 1. Sine operator simply decode or codes it into 1. If they're exactly the same, it codes this to be 0. If yi is less than mu, I simply have a minus 1. It doesn't matter what the quanta of yi minus mu is. And in the denominator, I have twice the frequency of the level of mu that I am, talking about, the mean, the occurrence of mean in this distribution, right? Okay. Now, we also know, so we can write the mean as just the population mean, y bar, sample mean is equal to population mean plus 1 over n summation I equals 1 yi minus mu. Why is that? Well, because summation of deviations from mean are 0. Okay, so in your basic statistics course, you must have learned that summation of deviations from mean in any given sample will turn out to be 0. It has to be equal to 0. Okay, so y bar is simply equal to mu. We are simply writing this term to be able to create a link between y bar and y tilde. Then we take a difference between mean and median, right? That's what we are after anyway, mean minus median, right? So this is the difference between mean and median, and we can write it approximately as 1 over n summation I equals 1 to n, the deviation from mean minus the sign of deviation from mean normalized by the frequency of the mean, the population mean itself. Okay, this provides us a measurable metric of y bar minus y tilde. What does it depend on? Right, it depends on, it's a function of the size of the data, it's a function of the population mean, it's a function of the frequency of the population mean, right, and it's obviously a function of the yi's, right. So it depends on these parameters, so it depends on the population distribution parameters and the size of the sample and the values that you are attaining in the sample. So this difference is very sample specific. That's the point that I'm trying to make here. Okay, all right. So moving forward, when yi minus mu is Gaussian, Gaussian means normally distributed, right? So if yi is normally distributed, yi minus mu will also be normally distributed because mu is simply a constant, right? So it's my yi minus mu will simply be following the distribution of yi with zero mean and the variance of exactly equal to yi. We can write that the variance of y bar minus y tilde, right? So now, remember in the previous slide, we wrote down the mathematical measure for y bar minus y tilde. Here we are writing the variance of y bar minus y tilde. Remember, we said that if you have a sequence of random variables, the mean of those random variables or realizations is also a random variable. And it turns out so is the median. So if the mean is a random variable, the median is a random variable, their difference will also be a random variable. For every random variable, we have a variance measure which provides us the error in estimating that value. So this difference has a variance value which can be written as sigma squared over n times this factor 0.57, which provides us with a statistic u, which is nothing but y bar minus y tilde divided by 0.75 sigma over root n, right? So this 0.75 sigma over root n is nothing but the square root of sigma squared over n times 0.57, right? Which is nothing but square root of variance of y bar minus y tilde. So what we are really saying is we are defining this statistic u as y bar minus y tilde over square root of variance of y bar minus y tilde. Okay. So this is a statistic. We have a data set, we have the mean from the data, you have the median from the data, you can calculate the variance from the data, right? Variance of yi minus y bar, because you have sigma squared can come from the data, n is just the size of the data set, and 0.57 is just a constant. So u is indeed going to be a number that you are going to be able to, back out from the data. So if I go back 2 steps from here, what I should be able to do is wherever I have a mean and a median for the row, I will also have a y bar minus y tilde, and I will also have a u for the row. So I am going to have ui's, where I is just a representation of rows, and similarly I am also going to have a y bar minus y tilde for each column, and I am going to also have uj's for different columns. Okay, so I am going to be able to build this statistic that is going to signal trouble when or not y bar minus y tilde is a large enough value. Okay, so that's what we are trying to get at. So we are now looking at u's being characterized or summarized for each row and each column. So I don't have to go back and look at each of these values, visualize whether mean is very much farther away from the median or not, and so on and so forth. I can just evaluate a u and it will summarize for me, the statistical difference between these values. Now sigma squared, I said that you can back it out from the data. It's just 20 over 27 and into interquartile range. The interquartile range is just a difference between the 75th percentile and the 25th percentile. How to get them? Well, just order the data from smallest to largest. The 25th value in a when you are the 25th step, that is the 25th percentile. When you are the 75th step, it's a 75th percentile, right? So 25th percentile will have 25% data which are below this value, right? And 75th percentile is one where 75% of the data are below or lower than this given value when by 75th. Okay, so IQR is nothing but y75 minus y25, multiply that by 20 over 27 and you have your sigma hat. Now notice that u is the standardized mean median difference, and whenever u is going to be greater than 3, a researcher should pay attention for outlier values. So what I've done is that I've defined U to be y bar minus y tilde over square root of y bar minus y tilde. And whenever I find modulus of U, which is nothing but modulus of y bar minus y tilde over square root of variance of y bar minus y tilde, okay, the denominator is obviously always positive. The numerator may be positive or negative. We are taking an absolute value. So it will always be a positive number that we are going to look at. Whenever this is greater than 3, we should be worried for outlier values or troublesome values, right? We should start to scan for them more closely in the data. Okay. Now, the point is that, what it does is that if I go back to my row and column summaries, I can simply, look at the data and I can just figure out U and then mark out the rows and columns where U is greater than 3 or somewhere around that value, right? So that's what we are going to do next. So we again have our data. We are going to figure out U for 23rd row, starting from the U from first row, and we are going to figure out U for the first column, all the way U to the 16th, 16th column. Sorry, it's going to be here. All right, this is probably the 14th column here, right? So we are going to figure out these U values in a table and see whether or not they are greater than 3. Okay, so let's do that. So here again, coming from Cressy's book, we have the standardized mean median difference, which is standardized mean median difference basically is y bar minus y tilde, mean minus median, divided by variance of y bar minus y tilde square root, right? This difference, which is just U, is now outlined here. So row 1, the U value is minus 1.54, much lower than 3 or minus 3, right? So absolute value is 1.54, much lower than 3, no problem. Okay, 0.40, no problem. 6.12, huge problem. We should be extremely worried about this particular row. 4 minus 0.45, no problem. Minus 0.35, no problem. 2.01, okay. 0.56, 0.07, 0.63. Minus 0.18, 2.12, 0.8, 0.46, 0.1, 1 point something, 0.6, 1 point something, 0.18, 0.35, and so on and so forth. So I've just circled the values that I want to be careful about. So clearly we have 6.12, 3.17. I've also circled 2.87 because it's quite closer to 3, and also 2.47 because, I think, why not just check it out. So what I really want to now look at in my data set, I'll go back and look at rows 3 and 23 and columns 5 and 12, where this 3 and 12, row 3 and column 12 are clearly problematic, and columns 5 and 23, let's pay attention to them. Okay, so let's go and make sure we remember these values. So I'm going to look at rows 3 and 23 and columns, I remember 12, it was I think 5 and 12, yes, so 5 and 12. So row 3 and 23, okay, so row 3 is right here. I go through row 3, I have 9.64, 9.52, 10.06, a higher value of 12.65. Okay, a candidate for an outlier. I should use my, green color. Okay, so 12.65 is a problematic value because it's lying around this region, which is, in this row, everything is 9. Again, coexistence seems. How come you had such a high value and then a drop right after that? Right? Okay, so my row 3 and row 23 has my 11.86, right? So this is the value that we talked about, right? I mean, if you go east to west or towards south from this value, 11.86 sort of stands out, right? And that is also predicted by my, U variable, okay? Columns 5 and 12, column 5, again, it has this very high value of 17.61 and it has a high value of 12.80. I'm just going to circle them. I am flagging outliers so that I can look at means and medians, etc., etc. What if I were to drop these values? How will the mean change? How will the variance change? Will they be robust or not? Column 12 is again, we have 11.86. So 11.86 turns out to be a value which, if we were to just look at the stem and leaf plot, we might not find this value to be very problematic, right? But as soon as we move on to sort of looking at this more sophisticated mean minus median based U statistic, this value which might not otherwise pop out, right, turns out to be a candidate for an outlier. This points out to a very important difference between spatial data and non-spatial data, right? In space, we are comparing the values from our neighbors and saying that, look, we are sampling coal. How different are you going to be at a particular location? Can you be really different? You can have a gradient where the coal ash percentage is slowly rising towards north, or slowly rising towards south, or towards east, or towards west, and values on the eastern side are greater than values on the western side. It can be a trend. That's a spatial heterogeneity measure. But in a locality, do you really expect to see a very different coal sample than its neighbors? Well, probably not. And that's the concept that this U statistic is mobilizing or using to come up to signal or guide us as researchers or statisticians or data analysts to this value of 11.86, which does not turn out to be a value that you want to sort of leave out without attention. Okay, so let's move forward. Okay, so now we are going to look at the third methodology for detecting outliers, and this is this methodology depends on the belief of local stationarity. So when I say local stationarity, I am basically saying the thing that in a locality I expect things to behave normally with respect to each other, and if I see abnormal behavior in a neighborhood, well, probably I should be becoming more more attendant to such a phenomenon, right? So what I'm looking at now, what I'm going to now propose as a device to do that is called as a bivariate scatter plot between Z at location S and Z at location S plus HE. Now, in spatial data, every data point is indexed by a location, right? So Z of S is simply the value at location S. So I can go to any location, call it S, and the value that I see there, that is the coal ash percentage, is going to be Z of S, right? Sorry about the, okay. So the value here at location S is Z of S, all right? Now, what is Z S plus HE? Now, E is called as a unit length vector with a given direction. So, E is a vector, it has unit length, so it is a unit long, right? When you multiply E with H, you are going to move H units in a given direction, and this direction information is contained within the vector E, right? So, the unit length vector, the purpose or the reason that we sort of use this notation of unit length vector is to contain the information on direction in which we want to move, right? H, on the other hand, is the size of the hop that I want to take from a given location S, right? So H is set to be 1. So I'm going to move one step at a time, right? So E will tell me, okay, if I'm standing at S, I want to move one step in, left so that I can get to S plus HE on the immediate cross on the left, right? If I go one step south or one step towards the downward direction, I'll have my cross that I go, which will become S plus E. E now is just southern direction, right, or downward direction from the S one step in that direction, right? So what we are going to do now is that we are going to create scatter plots of pairs of values where I go to a location, I take one step, one hop, I record that location, and then I create a pair of these things, right? So I'm creating a pair of ZS and ZS plus HE, and then I'm going to now present a scatter plot for these things, right? So pay attention to what I just said. I'm going to have ZS, it's going to be my x direction. So S is in x direction, right, x-axis. S plus E is in y direction. So I'm moving northward, right? So I'm basically starting at each value in my data, right? So let me go back to my data set. I'm going to start at 10.59, that's my Z of S, and I'm going to move one step further, Z S plus 1, right? And then, I'm going to sort of have 10.59 on the x-axis and 9.59 on the y-axis, and I'm going to point out the coordinate, right? So let's do that. So I have my 10.5 somewhere around here and my 9.5 somewhere 9 point something here. So this is a approximate sort of pair of ZS and ZS plus E. Each point on this scatter plot is representation of neighborhood pairs when we move in the east-west direction. Okay, so we are moving in the east-west direction. So basically in that data set, if I go back to my data set, I'm moving from 10.59 to 10.43. So I'm going to be looking at a pair between 10.59 and 10.43, right? But the ultimate purpose is that when I look at a value, right, and I just step one step further from that value in any direction, local stationarity, the belief of local stationarity basically suggests that I shouldn't be looking at a very different value in the locality, right? Again, it's coal lying under the ground. How different can you be? Can a value or coal ash percentage can you get if you just walk one step forward towards the eastward direction or towards the westward direction, towards the north direction or the south direction? It's just one hop, right? So whenever, we see values that are standing out from this bivariate scatter plot, right? That is a signal of outliers. For example, if I get a value of, when I'm standing at around 11 and I get a value of around 18 as the next step, when I move one step in the east-west direction, well, I should be worried. I'm looking at something very bizarre, right? If I go back to my data set again, I am basically starting out at 10.87 or 10.82 and ending up onto the next hop being such a large value of 17.61, right? So that signals trouble. So in this bivariate scatter plot, whenever I see values that are outstanding, which are going away from a cluster, right? A cluster that sort of represents a Gaussian, right? A Gaussian behavior, like a bell curve. There is high density in the middle, and then towards the peripheries, the density will die out. But if you see values which are much farther away from a, from a perceived periphery, then you should mark them for outliers, right? We can do this in the east-west direction. We can also do this in the north-south direction, right? So in the north-south direction, again, I am seeing the same pattern. There is a high density in the middle, and as I move out in any direction, the density sort of starts to die out. So there is some Gaussian behavior going on in every direction from the core of this bivariate scatter plot. So I can sort of draw a peripheral boundary, but there are some points that seem to be sort of off of this peripheral boundary, right? So this is the third methodology to look at scatter plots between Z at location S and Z at location S plus E, and these scatter plots provide us a signal of whether or not we should be worried about, outlier values. Okay, so we have seen three different methods of detecting outliers, right? So I'm going to call them three devices to detect outlier values, right? The first device was I'm just going to call it a histogram. We looked at a stem and a leaf plot. The second device was this U statistic, which was based on the difference between the mean and the median, and we did this row wise and column wise. Third is a bivariate scatter plot, which is sort of testing the assumption whether or not the data are locally stationary, right? So we mobilize this concept of local stationarity in the data. We will study stationarity in detail, but you get the idea of local stationarity, that we are ultimately looking at cold data. And if you're looking at cold data, we can expect some kind of a normal behavior, and as soon as we see something abnormal through any of these devices, we mark it for trouble. Okay, so here are these these values that I have circled in blue and green, and they are basically a set union of the outliers that we detected through these three different exercises. I mean, there is this 12.65 which I actually detected during the course of this lecture, but I guess these 1, 2, 3, 4, 5, 6, 7, and 8 values are the ones that we should be quite worried about, right? Going forward when we analyze these data, whether we are predicting, we are predicting in space values that we have not sampled, right? Or we are simply evaluating the mean of coal impurities, the average coal impurity in different directions, in different locations, sub-regions in this region. We should be very careful about these values. What is special in this analysis that has come from this second U statistic is that the value 11.86 is very similar to values like, let's say, 11.62, but 11.62 does not turn out to be an outlier through all these three different devices that we evaluated, right? So it's not always trivial, straightforward, or something that you can simply with your naked eye just go in and look at the data and you'll be like, oh, here is an outlier, I can look at it. Oh, well, you can do that. That's a good starting point, and we should always do that, right, as a starting point as data analysts. But we should probably also go one step further and work with formal devices or formal measures which will provide us an understanding of abnormal behavior in spatial data. Okay, so that's it for this part of our lecture. As a next part, I'm going to look at a case study where we are going to move away from this textbook data set and look at a real world data set for groundwater levels in India. And we'll see how, when we move from a textbook data set to a real world data set, some of the interventions are necessary before we can, analyze this data set. So look forward to having you again in the next lecture.